Astronomy is a science built almost entirely on interference because the universe does not allow controlled experiments. And so every claim must be extracted from motion, geometry, and the quiet existence of equations that refuse to balance unless something unseen is allowed to exist. When astronomers observe a galaxy, what they are truly observing is gravity in motion, because every star's orbit is a measurement and every velocity is a clue, pointing toward the mass that must be present to hold the system all together. Nearly 27% of all cosmic composition is dark matter, an invisible substance that responds only to gravity. Because at the largest scales of the universe, gravity rules. As dark matter gathers into massive halos, its gravitational pull captures hydrogen gas, igniting the birth of stars and galaxies. In the United States, Fritz Zwicky, Vera Rubin, and David Clow were three revolutionaries that changed the way that scientists saw the universe by implementing dark matter. In 1933, Fritz Zwicky demonstrated that the galaxies in the Coma Cluster were traveling at speeds too high to be held together by the gravity of their visible matter alone. He states that if this mass is confirmed, we would get the surprising result that dark matter is present in a much greater amount than luminous matter. The only explanation was that there was a vast amount of unseen mass that was providing the extra gravitational pull, because this was the same problem that appeared again inside individual galaxies. In the 1970s, Vera Rubin and Kent Ford found that stars orbiting the outer regions of galaxies move just as fast as those near the center, contradicting expectations based on visible matter. Once again, galaxies should have torn themselves apart. The persistent mismatch between gravitational predictions and observations revealed a deeper truth. Most of the universe's mass is invisible, and without dark matter, cosmic structures simply could not exist. The physics behind dark matter is inferred almost entirely through gravity, the force that allows for planets to have moons, stars to have planets, and galaxies to contain billions of stars. The paper, A Direct Empirical Proof of the Existence of Dark Matter, describes how scientists use gravitational lensing to map where the mass in the bullet cluster actually is, with gravitational lensing being the measuring on how gravity bends light from distant galaxies. The surprising result was that the strongest gravity did not line up with the hot gas, which contains most of the normal matter. The paper also reports an 8 sigma separation between the visible matter and the total mass, which is an extremely strong statistical result. This means that the difference is far too large to be explained by measurement error or just by simply modifying gravity. Because of this, the observation provides some of the strongest direct evidence that most of the matter in the cluster is invisible dark matter. Space is scary. The idea of physical objects far away that contain infinite gravity and that are able to overpower light itself. The idea of a luminous entity that powers life on the planet that we live on and burns through 380 sextillion joules of energy every single second. These are all the things that we can still have the privilege of seeing, even though we don't have the type of technology normally to see these while being physically present. But we can still see these with specialized telescopes. But dark matter is different. Dark matter is a form of matter that does not emit, absorb, or reflect light, meaning we physically can't see them through telescopes. Scientists detect dark matter through its gravitational effects on visible matter and light. Gravity depends on mass, which is described by Newton's law of gravitation. This equation tells us that the gravitational force between two objects depends on how much mass they have and how far apart they are. By observing stars, galaxies, and clusters move, scientists can calculate how much mass must be present to create the gravitational pull that we observe. For example, stars orbit around the center of galaxies because of gravity, and the gravitational speed can be approximated. If only the visible stars and gas existed, stars farther from the center should move more slowly. But when astronomers measure these speeds, the outer stars move much faster than expected. The only way the equation works is if there is far more present mass than we can see, forming a large halo of invisible matter around galaxies. Another powerful way to detect dark matter, which was mentioned before, is gravitational lensing, predicted by Einstein's theory of general relativity. Mass curves spacetime, and light follows that curvature. The bending of light can be approximated by alpha equals 4gm over c squared times b. By measuring how background galaxies appear stretched or distorted, scientists can map the mass causing that bending. In galaxy clusters, these gravitational lensing maps often show that most of the mass is not located where the visible gas and stars are. Instead, the majority of the gravitational mass is invisible, providing strong evidence for dark matter. Without it, galaxies would likely not have formed the way they did, and the universe would look completely different from what we observe today. Understanding dark matter is one of the biggest unsolved problems in modern physics. Scientists around the world are building new telescopes, particle detectors, and space missions to try to identify what dark matter actually is. In the real world, discoveries like this push the limits of technology, mathematics, and physics, often leading to new innovations and a deeper understanding of the universe we reside in. So the challenge moving forward is clear. We know dark matter exists because of its gravitational effects, but we still don't know what it's made of. The next generation of scientists, engineers, and researchers will be the ones to help answer that question. Dark matter is necessary because without it, the universe we see could have not existed. Galaxies would not have enough gravitational glue to hold themselves together, and galaxy clusters would disperse, and the early universe would not have formed structure fast enough to match observations. What really makes dark matter especially uncanny is how real it appears while remaining fundamentally unknown. It passes through ordinary matter almost effortlessly, and it does not clump into stars or planets, and it forms vast, ghostly halos that dominate galaxies. Some theories even question whether dark matter exists at all, proposing instead that gravity itself behaves differently on large scales. Yet every new observation continues to reinforce the same unsettling conclusion. Something invisible governs the universe, and until we understand dark matter, our picture of reality remains deeply incomplete. We do not merely observe dark matter at cosmic distances, we orbit within its influence. Dark matter enters modern cosmology not as an assumption, but as a conclusion, forced by equations that refuse to work without it, because orbital motion, space-time curvature, nuclear physics, and cosmic structure all independently converge on the same invisible component. We may not yet know what dark matter is made of, but we know with confidence how it behaves, and the universe continues to obey gravity as if it exists. The stars are what we see, but what holds them together is an invisible architecture, written not by light, but by gravity.